thank you. As already mentioned, I'm based currently in Paris, but some of this work was, well, most of this work was done when I was based in the UK. So just, I've been to a few places in Europe, so this work was not done in France, but my affiliation is currently in France, and is somewhat related to the very first talk that we heard. So some of these slides might look familiar and quite similar to the one for the first talk. This is roughly what I'm going to talk about. So I'm going to present some motivation for developing these sort of methods, briefly recall what particle filters are and what SMC is, that has been mentioned earlier on, the extension that we work on, which is called divide and conquer SMC, and finally, how we can apply this to filtering. So roughly speaking, the sort of data that we'll be looking at are what I call spatiotemporal data. They go under other names, but this one I particularly like it because it to me is quite clear what it does. So this is one example coming from this 2015 paper, and these are time series. So we have several years, and what the picture is showing is the amount of rain that fell in certain locations in North America. So what we want to do is, given this observation of amount of rains, to recover the probability of a particular area lacking water at the present time. So as you can see, we have a temporal component given by the years. Actually, I took 3 consecutive years, but the data are daily data. But we also have a spatial structure given by the grid over here. And in this case, it's a real spatial structure, meaning geographically based. One other example is financial data. So these are 6 exchange rates against euro. And again, what we observe are the exchange rates, but what we want to recover are the factors driving the volatility in the markets. And in this case, we again have a temporal component given by consecutive days, but we also have a spatial component, which factors in multiple items, including geography, clearly, but also political closeness and economical considerations. All of this data can be modeled as a state space model, which we already seen. So just to briefly remind you, I'm using a slightly different notation, so it's still good to look at this slide for a little bit. So I'm considering state space models with a latent process X, which is Markov, evolves in discrete time and has a transition density that I will call F, and conditionally independent observations, which are called Y's, and have likelihood G. So for the purpose of this talk, what I'm going to be interested in is recovering this sort of distribution, which is the distribution of all states given all data up to the current time. It has a recursive structure, so it can be written in this form, but for simplicity for this talk and also for some computational considerations, we mostly focus on the last time step. So the filtering distribution that we will be talking about is the probability of observing xn given all y's in the past. Now, as already mentioned, if we have a linear and Gaussian model, this filtering distribution can be computed analytically in the sense that we can use the conjugacy properties of Gaussians to basically recover the covariance and the mean of these Gaussians at every time step. Also, if we work on discrete spaces, there are ways to recover this distribution analytically, but very often this is not the case. If we are far from linear state space models and we don't have Gaussian distributions, we cannot compute this quantity, mostly because there is a normalizing constant here hidden by this sign, which is intractable when we have these sort of distributions. There are a bunch of things that we can do, but I'm going to be focusing on the particular models that I'm interested in, which are these spatial state space models. And by spatial, I mean that we know, like in the case of rainfall, that there is an underlying grid. So this is a three-dimensional structure where we have time on the horizontal axis, and each slice of this cube is one latent variable x. So we know that x is in RD, but has some sort of grid structure. And you can imagine that this grid structure is given by the sensors recording the amount of rain that falls into any location. And we can imagine that because of this structure, neighboring nodes have high correlation, but nodes that are very far apart have smaller correlations. And this is exactly what happens when we have this sort of geographical data. So this is to give a bit of motivation on why we particularly care about the spatial data. And now, as I mentioned, I'm going to introduce some very, very basic ideas on SMC and particle filters, because they will be needed to develop the algorithms that we worked on. So an alternative to the Kalman filter, when we don't have linearity or Gaussian distributions, is to use Monte Carlo methods, particularly sequential Monte Carlo methods. So what they do is they take the distribution that we're interested in, and they approximate it with a set of samples, the x and i's. They are samples, and they have associate weights, which are positive and sum to 1. I'm going to switch between samples and particles because very often these samples are called particles, hence the terminology particle filters. But basically, these algorithms are recursive. They mimic the recursion that produces the distribution. And so what happens is that to move from time n-1 to time n, we're going to use the transition density of the state space model to move forward in the future. Once we have done this, we use the observation likelihood to assign a weight to our new samples. This is because we have observed data, and so we want our particles or samples to be a good representation of the data. And then we apply a resampling scheme to obtain an equally weighted particle set. So a resampling scheme, you can imagine of it being just drawing from a multinomial distribution in which these are the outcomes of the distribution, and the weights are the probabilities of observing each outcome. I will have a picture in the next slide to try to give some more intuition on this particular set of algorithms. But what I represented over here, it was what is normally referred to as the bootstrap particle filter. And there are more sophisticated particle filters, but the key ingredients that appear in all of them are these ones. So we're going to need some transition density to sample from, a way to compute the weights, and a resampling scheme. These are the three constant steps that we see in all SMC algorithms. So this is a bit of a cartoon of what is going on, just to give intuition. So my particles are the 20 blue dots that are equally spaced in the first line, and I want them to be a good approximation of the black density. So clearly at the beginning, they are not a very good approximation of this black density because they are equally spaced over 0, 1 plus epsilon. So the very first step, we apply this transition density. Sometimes it's called a mutation density. It has different terminologies depending on the field of application. But what this is doing is just moving my samples around. Then once we have done this, we have the observations, we have the likelihood of these observations, so we can assign weights depending on how good our particles are. So you cannot see them anymore, but these dots over here are still there. They're just much tinier because their weight is very low. On the other hand, these particles over here, which are close to the high probability region, have a high weight, and so they are bigger and visible. And once we have the weights, we apply this resampling mechanism, which basically replicates the good particles, so those that had a high weight, and kill the other ones. So there are no particles anymore in this region over here because their weight was basically zero, and we have multiple copies of those that were over here. So roughly speaking, these are the three steps: the mutation, reweighting, and resampling. And what I'm going to talk about is an extension of this algorithm in which these three steps appear with some extra complications. So you might wonder, why do we need this sort of machinery to solve state space models? Well, the main motivation is pretty much given in this slide, is that when the dimension of the state space model is large, as you can imagine is the case for spatiotemporal data, we know that the mean squared error, so this is the filter mean, and this is our approximation obtained with sequential Monte Carlo. And so what I'm computing over here is just the mean squared error, will decay with the number of particles, so that's good news, but the constant that we have over here is exponential in the dimension. That pretty much means that you need a number of particles that grows exponentially with the dimension to guarantee good results. And this is just not feasible in practice. It's too expensive, and we cannot even store these particles. So we need some way to improve the bootstrap particle filter to tackle these high dimensional problems. I'm going to talk about one option, but there are many others that I'm not going to cover in this talk. So the option that I'm going to talk about is the divide and conquer SMC, which was introduced in a 2017 paper, and is an extension of standard sequential Monte Carlo, in the sense that while SMC evolves on a line, so moving from time step n to time step n+1 and so on, as I had in this cartoon of sequential Monte Carlo, in this case, we look at trees. So we have several leaves, and we want to move from several leaves to one root node, which is denoted by R. If you forget that this tree has all these nodes on the right side, and you only look at the line that moves from gamma u1, gamma u, and so on, then my tree is really just a line, and so I would fall back on standard SMC. This tree structure was motivated by considerations in distributed computing, but it turns out it's quite useful to deal with spatial models as well. So once we have this tree structure, in the end, what we do is not very far from SMC. So we still have several sets of weighted particles. We have one for each leaf. And we still use the usual SMC ingredients. So we will need a transition density, a reweighting step, and resampling. So reweighting and resampling are identical to those for standard SMC. The transition step, now, instead of moving from time n to time n+1, I'm going to move from the children of a given node to their parent. So I'm going to simplify things a little and assume that I work with binary trees, which means I have a left child and a right child. So taking the left and right children, I'm going to use them to propose something at the level of u, which is the parent node. And then because of the tree structure, we will need some way to take care of the merge operation over here. So if you imagine having one set of weighted particles on the left, one set on the right, we need to pull them together somehow. That's exactly what I'm going to try to describe in this slide, which is a bit heavy, I'm aware, but really this merging procedure is the key point in divide and conquer SMC. So the starting point, as I already mentioned, are two sets of weighted samples, one for on the left and one on the right. What I'm going to do is build this, which is called a product form estimator. And what it does is approximating the product of the marginals. So if I have my distribution on the left and my distribution on the right, I take the product and I have an approximation of the product of the marginals. Clearly, unless I have full independence, the product of two marginals is not equal to the joint distributions, which is the gamma u. So to account for this difference, we compute these weights, which are really just evaluating the mismatch between joint distribution and product of the marginals. Once we have these weights, we apply again the resampling scheme, which again, you can imagine it to be just sampling from a multinomial distribution. So how do we apply this to spatial-temporal data? Well, first we need to come up with a tree, but because we have this spatial information and we know that we have a grid, we can just decompose this grid following a tree. So this is what happens if I have dimension 8. I'm going to start with 8 leaves and merge them 2 by 2 until I pull them all together. So the algorithm works from leaves to root. At the root, I have exactly the distribution that I care about. And at the leaves, I will have some auxiliary quantities that will help me solve this problem in an easier manner. And how this works in the end is that I repeat this for each time step. So I have one approximation of my filtering distribution at time n-1. I'm going to input these at the leaves, use divide and conquer SMC to move up the tree, and output at the root an approximation, still particle based, of the filtering distribution at time n. So just to demonstrate that this works and compare with some competitors, I'm going to be looking at a linear Gaussian model, which the reason why we do this is simply because, as I already mentioned, we can compute everything we need in closed form using the Kalman filter. So I'm going to report the relative mean squared error, which is just the mean squared error divided by the variance. Okay, so there are a couple of algorithms on this slide. There are 4 competitors over here, 2 versions of the divide and conquer algorithm that I just described, nested SMC and the space-time particle filter. The main takeaways are that if you see this red-orange line does not appear when the dimension gets very high, because that algorithm gets too expensive to run within a reasonable timeline. The other thing is that this green version of divide and conquer does not seem to be improving. So on the y-axis is the relative mean squared error, while on the x-axis are 100 time steps. So basically this is measuring accuracy, but the green one does not seem to improve if I increase the number of samples, so the number of computational budget. And that's something that we're looking at the moment. This algorithm, on the other hand, is cheaper to run, so there is a bit of a trade-off between accuracy and computational gains. The version that I described is the yellow line, which improves with the number of particles, but also for very high dimension and large n, it is very, very expensive to run. Nested SMC, on the other hand, seems to perform quite well, but it relies on very strong assumptions, which are satisfied for a linear Gaussian model, but they're not in general. And to give you an example of where this is not satisfied, this is a stochastic volatility model, which is quite common in a sort of finance and econometrics applications. The model itself is not important. What I wanted to point out is that while the evolution of the state is linear and Gaussian, the observation is very unlinear, very nonlinear, and well, there is a Gaussian multiplicative noise. So the Kalman filter or any version of the Kalman filter will not work very well over here. For the same reasons, the nested SMC algorithm cannot be applied to this set of models. These are some results, only comparing divide and conquer and the space-time particle filter. What I'm showing so the red line is the truth, because these are simulated data, and the black line is my filtering mean, with the shaded area around being the interquartile range. So this picture is not actually showing that divide and conquer is doing a really good job, because the filtering mean is actually quite far from the truth, but it is still doing a better job than the space-time particle filter, which is this bottom plot. because in this case, we can observe what I was mentioning earlier, that is the collapse of the particle filter. Very often, there is no gray area because we don't have an interquartile range. Everything is equal to the mean. So we are not able to quantify uncertainty at all. Finally, there is still a lot of work to do on these high-dimensional models and how to adapt divide and conquer techniques to them. But these divide and conquer algorithms are not limited to the filtering problem that I described today. They've been used to perform parallel computation, distributed computation. They've been used also for models in which this tree structure is intrinsic and not artificial, like in this case. For example, graphical models, phylogenetic trees. The theoretical guarantees are also available in some form or should be easy to derive by combining several technologies. But there is still, because this paper of divide and conquer SMC is only not many years old, there is a lot of open questions about this algorithm. And I think I almost ran out of time. So I want to thank you for listening and take any questions if there are any.
Very good. Thank you so much, Francesca, for a very nice talk. And then we have one question online on whether you have tried applying your algorithm to S&P 500 markets index, for example, and whether this would be usable in the case of cryptocurrency data.
So I have not tried to apply it. What I can say is that normally when you deal with these stochastic volatility models, what you really want to do is parameter estimation, which is not something I touched upon over here. We only look at filtering. So to get to parameter estimation, you will need to solve the filtering problem well, then solve the smoothing problem well, and eventually estimate the parameters. The results that we have at the moment on the filtering problem are not good enough, I think, to get confident results in terms of parameter estimation. And it's something that we're looking into, but these models are very often not very identifiable.
Do we have any other questions from the online audience? Yeah, please. Andrei, you raised your hand.
Thank you. Thanks for 3 great presentations. My short question to Jon and to Francesca. Are there any extensions? This is a Bayesian computation section like Alexander mentioned. Is there any extension, say, to ABC, approximate Bayesian computation, or even synthetic likelihood, or even INLA, so other computation approaches in Bayesian world? Thanks for Jon and Francesca in particular.
Francesca,
we should start.
And then Jon continues.
Okay.
Yeah, so what we did, we concluded more or less that it would be very interesting to look at combining it with INLA, but we haven't had time to do it as of now. But it should probably work.
Okay, thanks.
Yeah, so from my side, it depends a bit what you have in mind when you mention ABC. So there is ABC SMC, which is an ABC implementation using SMC. And in that case, yes, I think you could use divide and conquer to extend the ABC SMC framework. I think that would be very nice to do, actually. If on the other thing that came to mind, which I'm now realizing doesn't really make a lot of sense, is to have a likelihood that you cannot evaluate in your state space model, which of course it is the case sometimes, but because divide and conquer is already very expensive, if you put on top ABC to evaluate your likelihood, you're probably going to get an algorithm that is so expensive that you won't be able to run. So I mean, it is possible, but maybe too expensive combining the two for this particular like particle filters in which you cannot evaluate the likelihood.
Okay, thank you.
Thank you.
Right. Do we have any further questions?
I had a quick question for Francesca. It's just, is there any code available to play around with what you have done somewhere?
Yes, there is. So this is actually the filtering bit is a paper in Statistica Sinica, and there is a GitHub repo with our code. I can just send the link to the code in the chat if it's okay for everyone. It's publicly available, so just give me a second to find it.
Yeah, perfect. It would be interesting to just have a look at to see what you can do with it.
I think I sent it to everyone, but
Yeah.
if you don't.
Yes, got it. Thanks.
Very good. If I may, Francesca, if I may ask a question about this divide and conquer strategy, in particular about like the use of idle and not idle CPUs or resources. Do I understand correctly that as long as you move forward in this hierarchical tree, every time you move one step forward in the hierarchy, you reduce the number of CPUs you're going to use for your individual SMCs? Or
Yes, that's correct.
and then of course what happens is that you're going to have the total load of your cluster or computer which will decay exponentially, and which is nice on one hand, but on the other hand, if you don't use these resources simultaneously for anything else, then you're kind of losing all of these other CPUs effort. And just a very naive question, if you could think about like running a lot of parallel chains for as long as you have the budget and then doing this merge step at the very end, or if anyone has been doing that.
Is something that we've been thinking about, but as far as I know, it is still unclear in the literature of standard SMC if it's better to run a lot of chains, to run chains for a very long time, or to have a lot of nodes in your tree. So both of those are doable. I'm not able to say which one is better.